Welcome back. In the last lecture, I introduced the Langevin equation and discussed various nuances, various issues relating to the equation, how the expected value of the square of the velocity blows up, and therefore, we need to incorporate a damping term in that equation, and we therefore reduce the equation to the form that is given in the red box here. V dot is equal to minus gamma V plus L T, where L is the stochastic force, a force that acts at random intervals on and that represents in fact the collisions between the particles in the fluid with the Brownian particle, or the molecules of the fluid with the Brownian particle. And we express the statistical properties of LT as on the average over an ensemble. The average of LT would be 0. If it had a residual drift, that drift would be captured by the gamma term, and the autocorrelations at different points in time would be gamma delta correlated with a scaling that would take care of the magnitude of the impulse of the driving force, random force. I also obtained the solution of the Langevin equation in the form that is given on this slide. V t is equal to V 0 exponential minus gamma t plus integral of the noise term or the fluctuating force term with the exponential minus gamma t minus s. Right. Then we proceeded also to discuss the relationship between Brownian motion and the fluctuating force L t that represented the collisions of the molecules with the Brownian particle. We expressed dut as the L t dt, and then we investigated the properties of ut, and we found that ut had all the properties under the assumptions of this model, under the features of this model. Ut had all the properties that make it compatible with the definition of Brownian motion, and therefore we could it was Gaussian with 0 mean, and therefore we could express the solution of the Langevin equation for the velocity with a Brownian motion integral as V t is equal to V 0 exponential minus gamma t plus integral 0 to t exponential minus gamma t minus dws. This dws is nothing but the infinitesimal Brownian motion increment. Now, we proceed further. We obtain the path integral solution of the Langevin equation. We start with a few prerequisites. In fact, part of these prerequisites we have discussed earlier, but to facilitate continuity, we are quickly going through or quickly recapitulating these definitions, and then we will move on to the explicit derivation of the path integral for the Langevin equation. So, as far as moments of a distribution are concerned, if the distribution is normalized, then we have it as x n, expected value of x n, where x is the random variable, is equal to integral over all possible spectrum, the entire spectrum of values that the random variable could take, x to the power n p x, where p s is the relevant probability density function. We are talking about continuous density functions or continuous distributions which are more relevant to our context. Then the moment generating function, if you recall, is nothing but the expected value of j x. Earlier I used the expression T x, but now because we are having an application, or we are moving towards applications and functional integrals in terms of path integrals, we as a method of as choice or as a convention, we use j for the source term, and therefore we write z of j. Z of j is the moment generating function, is the expected value of expectation of j x, and that takes this form where p and x is the normalized probability distribution function. I am using this to discriminate between the to accommodate density functions which are not normalized, which are unnormalized density functions. We encounter situations like that when we do perturbative expansions. So, we need to be careful with that. and of course, we can recover the moments by taking derivatives of Z and then putting j equal to 0 in the resultant expression. As I mentioned, for a non-normalized probability density function p x, we define the normalization by z0, which is integral p x dx, which in the normal course would be 1. If the probability density function were normalized, z0 would be equal to 1, but in the event that the probability density function is not normalized, we have an explicit provision for z0. So, p n x, the normalized density function corresponding to p x, which is the unnormalized density function, can be written as 1 upon z0 integral p x dx. And for a non-normalized probability density function, we have another normalization factor creeping up as a prefactor. When we define Zj, we define Zj as 1 upon Z0 integral exponential Jx Px, and the expectation is defined with respect to the normalized density function, and therefore, we have a factor of 1 upon Z0 coming up outside the integral, representing the normalization of the given probability distribution p x to p n x, and the moments are obtained as in the earlier case by taking the nth derivative of z j and substituting j equal to 0. Now, as you can see from the expression for Zj is the Laplace transform of the probability density function p x. It is explicit here, quite obvious in this expression for Zj that it represents the Laplace transform of p x. And if you recall, we also had the characteristic function which was similar to the moment generating function, which happened to be the Fourier transform of p x. So, we have two different two variants really of the same expression. Zj is the Laplace transform of p x, and Cj, which is the characteristic function, is the Fourier transform of p x. For a Gaussian distribution, the expression for the moment generating function and characteristic functions take a particularly simple and a particularly valuable approach, valuable in the sense that we face this in a number of applications, and if we work it out by completing the square, we find that the value of Zj is found to be exponential Aj plus 1 by 2 g j square, where A is the mean of the Gaussian and g is the variance of the Gaussian. So, Zj is equal to exponential A j plus 1 by 2 g j square, where A is the mean of the Gaussian, g is the variance of the Gaussian. Then we have the cumulant generating function. This will also be used extensively when we study quantum field theory, and it is nothing but the logarithm, the normal logarithm of the moment generating function. Wj is nothing but log of Zj, and the cumulants are recovered in the same manner as the moments are recovered from the moment generating function by taking derivatives of the cumulant generating functions and then putting j equal to 0. The first few cumulants, as you can see, the first cumulant is the mean for the Gaussian distribution. Indeed, the cumulant generating function for the Gaussian distribution is j a plus 1 by 2 j square g. The first cumulant is the mean, the second cumulant happens to be the variance, which is g, and all the other cumulants, because the cumulant generating function for the Gaussian is quadratic, is only quadratic in j. The remaining cumulants would vanish. We only have the first two cumulants. The first cumulant is the mean A, and the second cumulant is the variance G. Now, we talk about generalization of these concepts that I elucidated right now. Instead of having a random variable x, we have a series of random variables x1, x2, x3, a vector. And now x is a vector, and the x1, x2, xn can be construed as the components of that vector. And similarly, j is another vector which has the components j1, j2, jn referred to a suitable basis, whatever the basis may be for the moment. We shall come back to the issue of basis in a minute. G inverse is a real symmetric positive definite matrix. Now, why real symmetric positive definite matrix? Because at the end of the day we want to establish a connection between G inverse and the probability density function, and as you know, the probability density function can be represented by a matrix which has to be real, which has to be symmetric, and which has to be positive definite. So, that is an important issue, and that will in fact count very significantly, that will count very heavily in the analysis what is to follow. The real symmetric and positive definite properties of G inverse would become very handy, very important in the subsequent analysis. So, to recap, x is now a vector with n components x1, x2 and up to xn. J is another vector with components j1, j2, jn, and G inverse is an n cross n matrix which is real, which is symmetric, and which is positive definite. Now, we define Zj. Our objective is to define Zj. Zj is now become a functional, because now it is a mapping from the space of vectors to the space of real numbers, and therefore, it now becomes a generating functional rather than a generating function. It maps an n dimensional vector j to a real number, and it has the form, as you can see here, it has the form which is given by this expression in the blue box. Now, because as I mentioned, G inverse needs to be real and symmetric. Now, the very fact that it is real and symmetric should ring a bell, and that bell is that we shall be talking about diagonalizing this particular matrix. Because it is real and symmetric, there exists a basis, and we can have an orthogonal transformation from the existing basis to a new basis in which this matrix G or G inverse for that matter will be a diagonal matrix, and the elements of the diagonal will be nothing else but the eigenvalues of the matrix G inverse and the corresponding vectors, which will the eigenvectors corresponding to all the degenerate eigenvalues will represent the basis in which this particular matrix manifests itself as a diagonal matrix. To repeat, because G inverse is real and symmetric, it can be diagonalized. It can be diagonalized by an orthogonal transformation of basis, and the basis in the diagonalized matrix corresponding to G inverse will be a matrix where the diagonal elements will be nothing but the eigenvalues of G inverse, and the corresponding basis vectors would be nothing but the eigenvectors corresponding to each of those eigenvalues. So, lambda alpha are the eigenvalues and the corresponding vectors are V alpha in the basis in which G inverse is diagonal. So, we call the diagonalizing, we represent the orthogonal transformation representing the diagonalization by U, and the various transformations that realize that occur as a result of the operation by the transformation matrix U will be in this form, which is given on the slide. X tilde is the new vector corresponding to the original vector x when operated upon by U. J tilde is the new vector corresponding to the original vector x in the new basis, in the basis in which G inverse is diagonal. X tilde is the vector corresponding to the vector x in the basis in which G inverse is diagonal, and the rest of the things also are similar. So, this is the diagonal matrix G diagonal lambda alpha, which is the matrix G tilde, which is the diagonal matrix, which represents the diagonalized form of the matrix original matrix G inverse. Now, the first important property is that due to this orthogonal transformation, due to the diagonalization of the matrix G inverse, the binary form X transpose G inverse X remains invariant. This is easy to see, as you can see in the blue box here. It's quite, the proof is quite straightforward. We clearly find that X tilde T G tilde inverse X tilde is equal to X transpose G inverse X. So, this transformation U leaves this binary this form X transpose G inverse X invariant. This quadratic form it leaves invariant, right. Now, because G tilde is G tilde inverse is diagonal, because G tilde inverse is diagonal and the only elements in G tilde inverse are the diagonal elements, which are nothing but the eigenvalues of G inverse. What do we get? We get X transpose tilde G inverse tilde X tilde is equal to summation of lambda alpha C alpha square. This is very elementary, easy to prove, and this is a consequence of G inverse tilde being a diagonal matrix with the elements lambda 1, lambda 2, lambda 3 along the diagonal. Similarly, J dot x is we represent J dot x in tilde J tilde dot x tilde, in that means this inner product is also worked out in the new basis, in the basis in which G inverse is diagonal, and we get it as, we represent it as C alpha d alpha summed over alpha, right. Now, because it is an orthogonal transformation, therefore, U transpose is equal to identity, and therefore, determinant of U is equal to plus minus 1. We discard the value minus 1 because we want to retain the positivity of the integration volume, and therefore, we restrict our choice to determinant U equal to plus 1, which implies the Jacobian is also equal to plus 1. Now, what happens to the transform generating functional? That is, we have to look at it very carefully. We started with the expression for the generating functional as 1 upon z naught, and this whole expression, the first equation on the slide, and when we do the transformation, when we represent Zj in the new basis, in the basis in which G inverse is diagonal, we have found that X tilde J G inverse tilde X tilde K will be equal to lambda alpha C alpha square summed over alpha, and J x j, that is the product of x, and the scalar product of x and j would be d alpha C alpha summed over alpha. So, these two values we have already in a sense worked out earlier, and these two values arise because of the transformation of the basis, and we get this expression which is the second equation on this slide. Now, we need to look at what happens. The next step is to take the product outside the integral and to leave out the summation here, and that is done because we can represent it the various what you call are independent variables, random variables. Each of these xi's which constitute the random variables, the components of x are independent, and therefore, we can replace this exponential of the sum of these random variables by the product of the exponentials, and that is precisely what we have done, and that enables us to take the exponential outside the integration. Now, when we do the Gaussian integration, it is quite straightforward. Again, we do the standard procedure of completing the square. We complete the square of this expression, which is the first expression on your on your slide, minus 1 by 2 lambda alpha C alpha square plus D alpha. We represent it in the form of a perfect square plus that extra term 1 by 2 D alpha upon lambda alpha square, and therefore we can when we do this Gaussian integration of the expression, this expression which is there in the box in this slide, when we do the Gaussian integration of exponential of this, because this is nothing but a Gaussian integration. So, we do the Gaussian integral of this exponential and we get two terms. This particular term 1 by 2 d alpha square upon lambda alpha will go outside the integration, and we will get this expression in the red box as a prefactor, and the z0 term, the normalization term will be this expression, which will not contain any term containing containing d alpha, because d alpha relates to j, and we are talking about z0 here. Z0 is nothing but zj with j equal to 0. So, this integral is in a sense split up into two parts. One part, the j, by completing the square, this integral is split up into two parts. One part that contains the j and that we can take as a prefactor, and the other part that does not contain the j, that represents the normalization z0, right. So, at the end of the day, what do we get? Zd is equal to this expression, because the z0 terms cancel out. One z0 is in the definition of zj. If you recall, one z0 is in the definition of zj. Let us go back. This z0 is there in the definition of zj, and the other z0 is what we have computed when we do this integration in the blue box. So, the two z0s cancel each other, and we are left with this as the ultimate value of zj. Zd is this product, and when we revert back to our original coordinates through a inverse orthogonal transformation, we get zj is equal to exponential summation over j and k 1 by 2 j g k j k. So, now this is the generating functional. Now recall that x is now a vector, j is now a vector, and g j k is a matrix, n into n matrix, real symmetric, and therefore, this expression for zj is summed over j and k 1 by 2 j of j, the small j is an index, g j k j k. And as far as the z0 is concerned, z0 can be simplified further. Recall that this is the normalization of the zj. Z0 is given by the product of alpha of this expression. This expression as you can see is clearly a very simple Gaussian integral, and it takes the value under root 2 pi upon lambda alpha, and therefore, when you have n such factors, when you take the product over alpha, n such factors, this under root 2 pi over lambda alpha gets multiplied by 2 pi under root 2 pi n times. So, that gives the numerator of 2 pi n by 2. The denominator becomes under root the product of the eigenvalues. The product of the eigenvalues is nothing but the value of the determinant, and therefore, we get this is equal to 2 pi to the power n by 2 divided by under root determinant g inverse, because the product of the eigenvalues is the determinant, and we is the determinant of the matrix of which these are the eigenvalues, and our matrix is G inverse, recall that, and therefore, we can write it in this fashion, but under root determinant G inverse is nothing but determinant G in the numerator, and therefore, we have the normalization factor z0 equal to 2 pi to the power n by 2 under root determinant of G. and the moments are given by this expression. As usual, we take derivatives with respect to the various j's corresponding to the moments that we want, or whatever moments we want, we take derivatives with respect to those particular j's and then put j equal to 0, and we get the expression for the moments. The important thing is that in the case of the Gaussian, only even power movements would survive, the odd power movements would not survive, because the exponent is quadratic in the components j, and therefore, the odd power odd movements do not survive, all odd movements vanish in fact, and only the even movements exist. And in fact, the even movements exist, the expression for the even movements can be written as in the form that is given in this box, and this is what is called the Wick's theorem. An example, as an example, I have this particular movement x a, x b, x c, x d. The expectation value of this expression is given by all pairings g a b, g c d, g a d, g b c plus g a c, g b d. So, and this is how we can work out the movements of complex quantities, complex statistical quantities, like vectors. And now we come to the continuum limit of what we have done just now. So far we have been talking simply about the discrete case, where we have and x and j take discrete values, the components are discrete, we have x equal to x 1, x is the ordered tuple, x 1, x 2, x n, and similarly j is j 1, j 2, j n. Now, we try to extend this framework to the continuum case. Now, we are given a function x t. Let us say we are given a function x t of time in the domain t contained in 0 to capital T. We need to work out a limit obtained for the we need to work out a limit of the generating function in the for the vector x j in the continuum limit that x j approaches x t, or x j takes the continuum form x t. What are the substitutions that we have to make? Let us look at that. First of all, we do a time slicing, which is what we normally very common to practice. The entire time span 0 to t is split up into very small infinitesimal time slices, each of length delta t, such that the total time interval t is equal to n delta t. Now, the important thing is, how will we invoke the continuity requirement, or how will we make time continuous? Well, we will make time continuous by taking the limit n tending to infinity, because n tending to infinity or delta t tending to 0, which would imply that the time slices, the discreteness in time is becoming so small that it is as far as mathematically concerned, it becomes a continuous timeline. So, we make these substitutions, an arbitrary x j, which was, let us say we started with an x j, or we had an x j in the discrete framework, would transform as in the continuum framework as x j delta t. Jth slice multiplied by the time length of each step. So, it becomes x at the point j delta t, x at the point j delta t, because we are having now j, this j, the index j is representing the number of time slices since the initial, since t equal to 0. So, number of time slices multiplied by delta t, the length of each time step, makes it x j equal to x j delta t. J is obviously can take the values, because x j is arbitrary. So, j can take the value 0 to n. At when j takes the value n, we have x n delta t, which is nothing but x t. Now, we take the limit n tending to infinity, delta t tending to 0, preserving the finiteness of capital T. preserving the finiteness of capital T. Similarly, we identify Jj as Jt and Gjk as Gst, and we obtain, after making all these substitutions, we obtain the blue box is what we had in the discrete framework. The blue box is what we had in the discrete framework, and the corresponding expression in the continuous framework we get is the expression in the red box. You can see that x j g inverse g j k x k is substituted by x x g inverse x t x t ds d t integrated. The summation is replaced by the integration, and j x j x j product is also replaced by the integral j t x t d t. Right. Therefore, Zj expression that we had earlier, after simplification, after carrying out the Gaussian integrals, we had was the first expression, the purple colored box, the first box on the top, and this expression in the continuous framework, it takes the expression one which is given in the red box. And the measure of integration in this context has to be mentioned. This is a path integral measure. Capital D of x t in the square bracket is the path integral measure. It is given by the limit n tending to infinity, the product of all the dxj's. Now, and what about z0? Z0 in our earlier case was n tending to infinity 2 pi to the power n by 2 determinant g 1 by 2. Now, this is very interesting. It becomes formally it becomes infinite, but however, the moments continue to be well defined, notwithstanding the fact that the normalization tends to blow up or approach infinity or diverge as n tends to infinity. The integral is called the path integral or a functional integral. So, now another example we have here is of the path integral or the functional integral. Now, let us look at something more about this. We have this the moments are obviously obtained by the same process, but now instead of taking the common derivatives, the Newtonian derivatives, we now take the variational derivatives, functional derivatives, whether and the functional derivatives are defined essentially by this expression. The functional derivatives are defined by this expression, delta j s upon delta j t is equal to delta s minus t. What we do is the Kronecker delta, this discrete delta is now replaced by the Dirac delta function. That is the most important property of these derivatives. Right, we will continue after the break.